This video explores the mechanics of non-adiabatic coupling and molecular dynamics, moving beyond the traditional Born-Oppenheimer approximation. Non-adiabatic coupling occurs when the Born-Oppenheimer approximation fails, allowing for internal conversion between electronic states. The standard model assumes nuclei move on a single potential energy surface, but in reality, nuclear motion drives amplitude transfer to another electronic state. It is important to clarify the terminology. Non-adiabatic coupling in a broad sense includes both first and second-order terms. The derivative coupling vector is the crucial first-order object driving amplitude transfer, and the non-adiabatic coupling vector is a distinct quantity used to characterize the branching plane. Non-adiabaticity is specifically the action of the nuclear kinetic operator, acting upon an electronic basis that constantly changes with nuclear geometry. It is not simply vague state mixing. Derivative coupling measures how rapidly the electronic wave functions rotate in Hilbert space as nuclei move. High derivative coupling, where small nuclear displacements cause massive changes in electronic character, enables population transfer. The fundamental governing equation shows that coupling becomes exponentially more important as the energy gap between states narrows. At exact degeneracy, the derivative coupling becomes a mathematical singularity. If nuclei are treated classically, the effective coupling is the time derivative coupling. This coupling depends on how the nuclear trajectory cuts through geometry space, meaning the non-adiabaticity of a region depends on the direction and speed of nuclear motion. A non-adiabatic transition involves 4 steps: excitation to an excited state, nuclear motion exploring geometry space, gap narrowing as the energy difference approaches 0, and finally, amplitude transfer driven by derivative coupling. The adiabatic representation has a diagonal Hamiltonian, and coupling appears through nuclear derivative terms. The diabatic representation has electronic states that vary smoothly, and coupling appears as ordinary off-diagonal Hamiltonian matrix elements. Diabatic models are often preferred for simulations due to computational stability. Conical intersections are the extreme limit, defined by exact degeneracy. The local topography is controlled by the branching space, defined by the difference gradient vector G, and the non-adiabatic coupling vector H. This is where electronic identity fails, enabling fast internal conversion. At the intersection, the derivative coupling D diverges as the energy gap approaches 0. However, the non-adiabatic coupling vector H remains a stable mathematical quantity used to characterize the branching plane. Non-adiabatic coupling, NAC, drives processes like internal conversion between states of the same spin. Spin-orbit coupling, SOC, drives intersystem crossing between different spin manifolds. The correct language for intersystem crossing is spin-vibronic coupling, where NAC and SOC work together. Welcome to this video on navigating the quantum funnel, focusing on a first principles playbook for emitter design and non-adiabatic coupling. We begin by examining the mechanics of state-to-state transfer. This involves adiabatic dependency, where nuclear motion alters the energy landscape. Next is the derivative coupling vector, which measures how fast the electronic basis rotates with geometry. Finally, velocity projection shows how coupling and nuclear velocity force the wave packet to transition. The danger zone for fluorophores involves quenching. Non-adiabatic coupling creates a shortcut for internal conversion from S1 to S0. When the wave packet is near a geometry where S1 and S0 are nearly degenerate derivative coupling spikes. This non-radiative decay pathway drastically reduces quantum yield and emission lifetimes. Our defense strategy is engineering rigidity to restrict access to the non-adiabatic region. Flexible molecules with large amplitude distortions often exhibit weak emission due to a fast track to conical intersections. In contrast, rigid designs physically block the motion required to reach the conical intersection, enhancing luminescence. In vibrational anatomy, we identify dangerous modes. The danger zone involves motion that simultaneously alters energetic resonance and derivative coupling. The safe zone includes benign motion that leaves bonding patterns and orbital overlaps largely intact. Decoupling excitons from high-frequency bond stretches can suppress non-radiative decay by nearly 2 orders of magnitude. Orbital engineering focuses on decoupling the exciton. For bonding character, the electron and hole are coupled and strongly perturbed by bond stretch modes. Utilizing donor-acceptor geometries creates a non-bonding or charge transfer character, where the spatially disjoint electron and hole are less perturbed, collapsing non-radiative loss. The TADF paradox highlights the double personality of non-adiabatic coupling, or NAC. NAC can lead to parasitic quenching via fast internal conversion. However, it can also facilitate spin vibronic risk, where vibronic coupling combined with spin-orbit coupling efficiently recycles triplets back to emissive singlets. Emitter design is about shaping the right couplings. The computational stack outlines a four-step first principles workflow. First, characterize states. Second, compute couplings, including derivative and spin-orbit couplings. Third, locate geometries like conical intersections. Finally, propagate dynamics using mixed quantum classical methods to evaluate the funnel access. The method selection matrix compares multi-reference and single-reference methods. Multi-reference methods are highly accurate for complex electronic structures, but are expensive. Single-reference methods are less accurate in certain regions, but are low-cost and highly scalable for high-throughput screening and initial dynamics. The first principles recipe involves a step-by-step process. We begin with initialization, followed by mapping same spin and different spin crossings. Then we compute couplings and project promoters onto normal modes to identify vibrational threats. Finally, we run dynamics to statistically estimate the outcome, emission versus funnel capture. Emitter design synthesis offers master heuristics. Weak fluorescence occurs if the conical intersection is low and accessible. Rigidity drastically improves efficiency by blocking access. Non-radiative decay is suppressed if the excitation is decoupled from high-frequency stretching modes. And finally, risk can be fast by optimizing the triplet landscape, even with poor direct SOC.